to represent Scilab lab for preclinical MRI pilot lab. I didn't choose this name, but all right. So we focus on the concept called molecular imaging. What is molecular imaging? In short, it's a non-invasive imaging of in vivo biological processes at the cellular or molecular level. I would like to emphasize the part in vivo, as in like we would like to image the biological processes in a living subject. Can it be a mice, rat, whatever it is, but we are interested in looking in a system which is alive. So to do this, we have the following imaging modalities. We have the first of its kind, PET 3 Tesla MR, then combination of SPECT CT, and then another instrument which is a combined facility of PET, SPECT, and CT. And we have a new inducted system for micro-CT, that's generally for doing bone scans. So I'm going to give you an example how we use this imaging modalities to follow an in vivo process. So I will just give just about the study design. So here we try to evaluate something called smart material. Smart materials are those which carries like special proteins, in this case bone morphogenesis protein, which helps in quicker bone regeneration at the site of surgery. Okay, so the aim is how good the system is, the carriers are. So the smart materials carry this protein, that protein should help in bone regeneration. So we use this following modalities to follow this process. To do so, we chose rat as an animal model. So we made like a fracture. I don't know, it was like a physician who does all the scientific work. I'm an image analysis expert. Just long story short, we had like control animals which had just the carrier material but no proteins at the site of fracture, and then the principals, they have the carrier along with the bone morphogenesis protein, which we want to evaluate. So the controls did not have any protein, the principals had the protein. All right, to follow the release of this protein, we radio label this protein with a long-lived radioisotope, iodine-125, which has a half-life of 60 days. All right, and this radionuclide can be detected by SPECT. The output, what we want to see as a final output is how quick the bone regenerates, right? So there is a fracture and how quickly does this fracture heals. So the output is bone regeneration. And to follow that, we use radio labeled fluorine. If you guys know that, like fluorine plays an important role in bone regeneration. So what we did is we just radio labeled the fluorine. And this, if the bone is regenerating, this radio-labeled fluorine will be taken up at the site of fracture, and which can be detected by PET. All right. And the most obvious thing to see the final output is to see if the bone is actually growing or not. And to do that, to visualize that, we used micro-CT. All right. So to start with, we have to position the animal in the camera. So we use the SPECT. So this is the site where we want to image. So we start with a CT scan, a simple CT, to position the animal. As you can see, the clamp that holds the fracture together. And then, so this procedure takes around 5 minutes. And then at the same position, we perform a SPECT scan. And it's a 2-head SPECT scan. And so we perform the SPECT analysis for 30 minutes. So this 2-head cameras rotate around the animal and try to accumulate as many this radiation gamma rays as it emits. Here I just want to emphasize that this radiation is coming from the already incorporated radionuclide in the surgery spot, this iodine-125. We are not injecting anything at the time of SPECT scan. All right, so we position the animal with CT, we follow the iodine-125 protein with SPECT, and now we want to see how the bone is growing, the rate of bone regeneration. So these are all taking at the same day. So first 5 minutes CT, the next half an hour is SPECT. Then we just move the animal towards the PET gantry, and we just do a PET scan. Oh, sorry. So this is how the final output might look like for you. So the bones, which are in the grayscale, and the radio-labeled protein, that's in the orange color, we can see. So this is 3 days post-surgery. This is how the image looks. So there is a retention of the protein at the site of surgery, and now we want to see if any bone is growing at all. So now we are moving to the PET part. This is the time where we are actually injecting like a bolus injection of sodium chloride. So this is like a special. The PET is something special. I just want to give a gist of how this PET actually works. This positron emission radionuclides, as you know, these are like unstable radionuclides. So they get the stability by converting a proton in the nucleus into a positron and a neutrino. This positron is nothing but like a positively charged electron. So we are talking about an antimatter right here. So this one, as it's emitted from the nucleus, it travels a small distance, and when it meets its, not like a nemesis, but like this electron, here the mass is converted into energy. This positron and electrons collision is converted into energy, and it releases two high energy gamma rays. Yes. So these gamma rays are detected by this PET. So this is like a sequence that just goes on. We run this PET scan for like half an hour. All right. And this is the beauty of PET. Here you can follow the kinetics of your tracer right from the time of injection, like in the vein, it accumulates in the heart, and through the iota it distributes to the different parts of the body. This is like an amazing thing to see. Like if you look at the image right now on the screen, you can see from the time of injection, the fluoride is getting accumulated at the site of fracture. All right. So here you can get the dynamic image from the PET as well as static. Like how does the tracer profile looks 30 minutes post-injection. So not just for visualization, you can also perform quantification with the PET. So you can get numbers, what's the tracer kinetics of your tracer at different parts of the body. And you can also use this data to perform kinetic modeling, which is much more important in the pharmaceutical industries. Yes. So we have that CT, SPECT, and PET. So now you have the PET data. This is 3 days post-injection. So then we did something like a longitudinal study. So we performed the same procedure on the same animal at different time points. And this is how the profile looked like. We follow the same animal 6 weeks post-surgery. So as you can see, there is like a release of, can I get the mouse? Yes. So you can see there's a protein, and then it gets like released into the stream. And with that time, since there is a protein, you could see a response as the bone regeneration. Like the rate of bone regeneration is getting faster and faster. Now, as for now, I'm just showing you about the principal animals. We also have the control animals. I mean, you should have like a reference to compare what is working or not. All right. So please pay attention. I mean, this blob is a urinary bladder, just to give an idea that this is a live animal. It is sedated, it's anesthetized, but we are working on a live subject. So this is molecular imaging. So on the left, you have the control animals, which just have the carrier, but doesn't have any protein, but the principal group, it carries the protein, where you should see a relatively faster bone regeneration. So with time, you could see like at the site of surgery, compared with the control, the rate of bone regeneration is relatively faster. And you could quantify this data with the PET as well. So we just show there's a rapid burst of the protein. As a response, you could see a bone regeneration. All right. Then we also did the micro CT, but on a different, like the time interval between these scans. We did a micro CT scan as well to see the actual bone growth. As you could see from the left, comparing the left to the right, this is the control, where you could see not much of a bone regeneration, but in the principal animals where you have the bone morphogenesis protein, you could see a response as the bone is growing with time. So this is how we use different imaging modalities. This is just to give a just like what kind of research we do on the platform. So you can use such non-invasive validation to validate your drug. Or like in a non-invasive, you can visualize, you can quantify. Here you can utilize this 3 R's of scientific research. I hope you know that, like to reduce, refine, and replace. So earlier such studies, they used to do like biodistribution studies. So you have to have like lots of animals. Per group, you should have at least like 20 animals to have such validations. And we just reduced the number of animals to like 4. We have published this data as well. So this is, I'm not just making up any stories. This is a published data. All right. But our major expertise at the platform is tracer development. As Frederick has shown, like amazing slides, and we have like a good collaboration with Affibody as well. Just give an example how we take a drug from bench to bedside. Okay, so this is just to give an idea, like a basic approach, how we conceptualize, how we develop a tracer. Okay, so now we are looking at a tumor. We want to visualize this tumor with nuclear medicine techniques, all right? So you all know what a biomarker is. Say if this tumor expresses something, specific biomarker, and these biomarkers are overexpressed on these cells. And if you could design something like an antibody that like specific to these receptors, and if you can radio label these ligands with any radionuclide, and if you can detect these signals, then pretty much you can visualize where the tumor is. Good to get this. So this is a basic concept. I mean, each step is by its own is like a PhD thesis. Trust me. Yeah. All right. So here this is the task. We want to visualize the insulin-secreting beta cells in the pancreas. Just to give an idea, so the whole pancreas, say if it's like 100 grams, 95% of it's like the exocrine tissue, and the 5% is endocrine. Within the endocrine, we are looking for islet cells, which constitute like 5%. We are looking at something less than 1 gram of cells that you want to visualize in a macro scale. Okay, your target, insulin-secreting beta cells. All right. So on these beta cells, it was already figured out that there is a biomarker, this GLP-1 receptors, which was thought to be like very specific to the insulin-secreting beta cells. And then we fished out something called exendin-4. That's the peptide which binds very specifically to this GLP-1 receptor, and we tagged this exendin-4 with a PET radionuclide called gallium-68. Okay. Maybe I'm talking too fast, perhaps. But just if you have any doubts, we can discuss it during coffee. So we have the facility to radio label these peptides. To start with, you should prepare this radio labeling of your peptides. I mean, if that fails, the rest of the pipeline is like distorted. So we have the capacity to radio label these peptides. This is just to show an example. So this peptide has been radio labeled with gallium. We perform extensive cell studies as well. We are capable of that. That's the basic step. But then we just take the next step towards the tissue samples. We have a small biobank. We have like the tissue samples from different animal species. In this case, we are interested in the pancreas. So here you could see we try to test on the different species pancreatic samples. But this is primitive. Right now, this is in vitro studies. When you're subjecting the tracer into just buffer, there is no such competition. It's just if it binds or doesn't bind. But what you want to do is to take it to the clinics. I mean, when you subject this tracer into your bloodstream, there are a lot of like tons of enzymes that can like cleave your proteins and other stuff. So the next step, if you find like if this is convincing, we take it to the animals. We start with the small mice scans, nude mice scans. Even to start with, we check the in vivo stability in the normal mice, just to see if it's good enough, if it's binding specifically to the organs where you're looking for, and if that's convincing, sometimes we take a tumor models as well. So we are looking at pancreas. Here you could see that we could significantly block uptake in the pancreas. I mean, islets are in the pancreas. And we also did a tumor model, this insulinoma tumor models. They express a lot of GLP-1 receptors as well. So this is another way to confirm that your tracer is specifically binding to the receptor that you're looking for. And also we work with a negative tumor model. This PANC1 cells, these cell lines do not express these receptors. If your tracer is specific to your receptor, you shouldn't see any uptake. And that's what you see. You don't see any uptake in the negative tissue model. So then we try to image this tumor models. So this is the baseline study on a insulinoma tumor model. As you can see, this tracer is excreted through kidneys. Unfortunately, these pancreas are very close to kidneys, and what we call it as partial volume effect, and so you cannot visualize pancreas in small animal models. But in the tumor model, this insulinoma tumor model, you could clearly see there is a quite high uptake of the tracer, and we were able to block it. But we need taking something to the clinic, you should always have something to compare with. Like if there is a tracer that already exists at the clinic, which is better than what you're working on, that's just waste of time. So at this point, we compared with the golden standard, which is called Carb11 HTP. Only 3 places in the world can actually synthesize this. Uppsala is one of them. They developed this technology. This is that was the most sensitive tracer for insulinoma. And right at this preclinical setup, we could clearly show that the current tracer is way better than the clinical golden standard. That was promising. So then we moved forward. Okay, we tried it on the rats. We escalated it. Here we did something called like dose escalation study. So you have like a baseline, say 100 units of your tracer. In the dose escalation study, you have like 100 units. You increase like 100 plus 200 units of unlabeled. What you're doing is a competition study. So upon increasing the co-label peptide, you could increase the competition and you could see the uptake in the pancreas has been decreasing. And then we also worked on a diabetic animal model. I mean, long story short, diabetic animal doesn't have islets. If your tracer is binding to islets, you shouldn't see any uptake in the diabetic animal model. Easy to understand? Yeah. So you don't see any uptake in the diabetic model. So it was bombastically fantastic until here. Rats, we're all happy. But do you think this is good enough to take this tracer to the clinic?
No.
Yes, okay. I understand. I mean, yeah. We did something called ex vivo autoradiography as well. So you injected this tracer into the animal, and after a while you take out the pancreas, you section this pancreas, and we expose this pancreas to the phosphoimager. So you should get the signal from the radionuclides. And the same section we try to stain it with insulin staining, simple immunohistochemistry. So if your tracer is indeed binding to the islets, they should like co-register. Yeah, until rats, bombastically fantastic. But still, since pancreas are close to the kidneys and this tracer is secreted via kidneys, it was hard to visualize pancreas. If I forgot to mention in the beginning, the aim of the study was to visualize these islets of pancreas and then to quantify them. All right. So, yeah, the team had a lot of money. So we did studies on monkeys, cynomolgus monkey models. So there, we did the same dose escalation study. So we just had like 100 units of tracer, then 100 plus extra units of unlabeled peptides. So with the increase of cold peptide dose, we were able to see that we were able to block the uptake in the pancreas. This was good enough. Here it shows that the tracer is binding to the pancreas, but we couldn't confirm this. The binding in the pancreas, is it indeed just in the islets or somewhere else in the pancreas? At that point of time, not at that point of time, even now, it's really hard to get ethical permission to make a monkey diabetic. So the team still had more money. They did studies on pigs. It was relatively easy to get ethical permit to make the pig diabetic. So long story short, non-diabetic pigs, they have islets in the pancreas. Technically, you should see uptake in the pancreas. Non-diabetic animals doesn't have any islets. You shouldn't see any uptake in the pancreas. Easy study design. Cool. So we started with the non-diabetic animal model. So we did a baseline scan. So it's like mostly like tracer, no competition. And then after that, we did a competition study, and you could see we were able to block it. Happy. Next. Oh, yeah, baseline and block studies. Okay, so this is the profile from non-diabetic animal. So we could see a specific uptake of your tracer in the pancreas. Bingo. Now we did on a diabetic animal. Any difference? This was one of the disappointing days in my life. I mean, yeah, life is tough. Sorry, what?
There's tracer. There is tracer.
There is tracer, yes, but it's binding the as I said, diabetic animals does not have insulin secreting beta cells. If the tracer is supposed to bind to the islet cells, we shouldn't see any uptake in the pancreas, but we see it. So once again, back to my question. It was bombastically fantastic in rat model, but pigs say something else. Which one would you believe? Yes. Yeah, I would say so as well. So yes. So this was the thing. At the baseline scan, we couldn't see much of a difference between these two models. So then we euthanized the animal. We did insulin staining and other stuff. This animal was indeed diabetic. All right. So yeah, but it was good in one sense. We were able to save a lot of money, so we canceled the clinical studies. It's just the way you look at things. Okay, so this is just a thing. So you need to be cautious when you're like try to extrapolate data from a preclinical to humans. All right, even though we are like genetically identical, the physiological and biological things and how things express in more relevant animal models plays a lot. So I haven't shown you any clinical data, but I have a data point on clinical. Why would we do a clinical study? Okay, earlier I showed you the mice model, so we tried it on an insulinoma tumor model. But if you remember Steve Jobs, he had the same insulinoma tumor. All right. At that point of time, this 5-HTP, that was a world sensitive tracer. So what I'm showing you is a compassionate case study. This lady was 35 years old at that point of time. She was diagnosed for insulinoma. Then what they did is the carb 5-HTP scan. The primary tumor is in the pancreas, the metastasis is in the liver. So, but there is, it's everywhere in the liver. So you can't look for the metastasis. If you don't know the extent of metastasis, you cannot start any therapy, even chemotherapy, right? So they couldn't even detect where the primary tumor was. In that case, they cannot do the surgery. They don't know the extent of metastasis. They cannot start the chemotherapy. They went forward with the surgery. The physician thought he found out the primary tumor. They did the surgery and other stuff, but but her blood glucose level increased again. So that shows that the metastasis has relapsed, as she's not completely cured. So they just did an FTG scan. 98 or 99% of all the diagnosed tumors, if I'm right, please correct me. All of them go through this FTG scan if they want to know if there is a tumor or not. Even that tumor fails in this case. So this is just to show you this insulinoma tumor is not a fast-growing tumor. I mean, basic story. FTG is nothing but glucose. This tumor cells accumulate. Their metabolism is relatively faster compared to the normal cells. That's the reason they take up a lot of glucose. If you radiolabel this glucose, that's what you see as an output in the FTG scan. All right, HTP failed, FTG failed. Until now, we had all this data from the monkeys, pigs, rats, and other stuff. So we asked Lackabadal-Sperkat if we can do this compassionate case study. The physicians took responsibility. Then we did the scan. This was half an hour post-injection. It clearly pinpointed where the primary tumor was. It showed you, it showed where the extent of metastasis was. This is one of the happiest days of my life. So this is just to show an example, these insulinoma tumors, as Frederick mentioned, there is a limitation with the PET, the resolution of human PET camera. Best scenario, what I know, is 4 millimeters. So if your tumor is say, 1 millimeter, that's a huge possibility. With respect to PET cameras limitations, you can't look at these tumors. But if you have a higher tumor to background ratio in this case, if you see the tracer uptake is almost nothing in the liver, it's just in the metastasis. In that case, you can visualize such small metastasis. Okay, as you know, this is radiation. If you want to take these things to the clinic, you have to perform something called dosimetry to find out how many scans can be done in a year. In this case, kidney was the dose limiting factor, so we estimated more relevantly from the patient scan that you could do at least 7 scans per year. As far as I know, per year any patient just goes through 2, maybe 3 to 4 scans per year. So this gets OK pass, so that you can do that in the clinical studies. So this is pretty much what we do at our platform. This is
Thank you very much.
The tracer.
time for one or two very short questions.
Yes.
So, if I understand correctly, it is still going to clinical testing?
Yes.
Okay.
Yes. If not for diabetes, for some other purposes, as in for insulinoma, as well as they transplant islets in the liver for the diabetic patients, the extreme cases. We are trying to understand why does the transplanted islets dies and all this stuff with this tracer. Yes. This is my PhD thesis, actually. Yes.
Does your lab or do you have any idea the discrepancy between the rats and the pig? Yeah, so why was there a difference in the results?
Yes, yes. Actually, it's been published. The structure of islets compared to the rats is different from the humans as such. The islets, they're like generally expressed on outer side of the islets of Langerhans, but in the humans, the islets, the beta secreting cells, they're actually inside. So yeah, better perfusion, like you have more variables to get the tracer into the animal. That's the reason. Yeah, but in this case, the physiology is apparently a little different. So what might work on the rats? Unfortunately, it work. Like most of the scenarios, it might work, but it's just that's the reason we always say you need to be cautious when you try to extrapolate data from preclinical to clinical, and you should have a lot of money to work this.
Okay, thank you. So.